object was really an amazing achievement.
It seemed undeniable. A giant black hole, and at the center of our Milky Way. But how could such a monstrosity come to be? One idea is that black holes are born out of the death throes of enormous stars. Like a red supergiant, a star 10 times more massive than our own sun. Deep inside, temperatures soar above 1 billion degrees. Helium and carbon fuse into heavier elements: oxygen, silicon, sulfur. Eventually, the nuclear reaction creates iron, and the core stops burning. Then, the star implodes under its own immense gravity and goes supernova. What's left is a heavy core of subatomic particles, a neutron star, only about 10 miles across, but of incredible density.
In fact, it's so dense that a teaspoonful of neutron star matter would weigh about 1 billion tons.
If the neutron star is heavy enough, 3 times more massive than our sun or more, the implosion will continue.
Eventually, the gravitational pressure will be so large that the neutrons themselves will be crushed, and there'll be nothing left to stop the collapse.
Many researchers believe that the Milky Way is littered with small black holes, the dark, dense remains of dead stars.
There must be millions and millions of black holes zipping around our galaxy as we speak. But we don't see them in general because they're dead. They're corpses, and there's nothing there to light them up.
They might be invisible, but to a visitor, these small black holes, maybe 10 miles in diameter, would be especially deadly.
One of the scenarios that always gets me thinking is death by black hole.
Approaching a black hole, the gravity is so strong and space is so warped, it distorts the light all around it. If it's a small black hole, then soon you'll be distorted too, by tremendous tidal forces of gravity.
The tidal force is the difference between the gravity at your head and your feet. The gravity at your feet, if they're closer to the black hole, is a little bit stronger than the gravity at your head, and you feel that as something that is tearing you apart.
Stretching you from head to toe. The tidal forces unrelentingly getting stronger as they exceed the molecular forces that bind your flesh, as you snap into 2 pieces, and those 2 pieces snap into another 2 pieces.
And ultimately, you will pull your atoms apart. You will be, as we say, spaghettified.
And so you end up moving through space-time like toothpaste through a tube. And if I pick a way to go, that's how I'd want to go. It's got to be better than just getting buried. I mean, come on now.
A supermassive black hole, 1 million times wider, might at first seem more inviting. Since it has a larger event horizon, the pull of gravity is more spread out.
If you go to a supermassive black hole, the tidal forces are weak enough that you can fall not only through the event horizon, but deep down into the interior of the black hole.
So, with a good spaceship, you might be able to cross the event horizon into the black hole itself. Now, thanks to a computer simulation based on Einstein's own equations, we can see exactly what such a trip would look like. The supermassive black hole is surrounded by swirling light beams as superheated gas rushes into orbit at high speed. Light and matter are suspended by centrifugal force, and then inevitably fall victim to the relentless pull of gravity. At last you cross the event horizon, the point where nothing can escape.
So let's imagine that we fall through the event horizon. That's the place where space is moving faster than light. We fall deeper down inside the black hole.
But don't expect the black hole to be black. Deep within, there's an inner horizon, a logjam of trapped light and energy.
At a certain moment, as we hit the inner horizon, there's this infinitely bright, blinding flash. And that's all the stuff that's been waiting there, trying to get out, is just held there at the inner horizon.
Unfortunately, you wouldn't have long to enjoy the view.
It would vaporize you. Roast you, vaporize you, marmalize you. Almost certainly, if you fell into a real black hole, you would simply, unfortunately, die.
Science fiction displays a bit more optimism, like the 1979 movie The Black Hole. Space travelers do indeed fear this massive object.
I will travel where no man has dared to go.
Into the black hole?
Why, that's crazy.
Cuckoo is a Swiss clock.
But even more cuckoo, the heroes actually survived their descent into the beast, where they're treated to a heavenly experience. Popular culture has cast black holes as the freaks of the universe. And the supermassive black hole at the center of our Milky Way, weighing in at 3 million times the mass of the Sun, seems especially monstrous. But is it unique? To find out, astronomers are probing distant galaxies to see if our giant black hole is one of a kind, or nothing special. The Sloan Digital Sky Survey is taking a census of the big galaxies within 1 billion light years. For every patch of sky, a steel plate is created. Each hole represents an entire galaxy within our view. Fiber optic sensors are plugged in. Each measures the distinctive spectrum of light emanating from a galaxy's core, and can detect signs of hot gas swirling into a black hole. You can see the results. Circled in red, virtually every major galaxy bears the signature of a supermassive black hole.
That was pretty amazing. Before that, we thought, yeah, maybe a large number of galaxies have black holes in them, but every galaxy has a black hole? That was something very interesting.
The closer we look to the centers of galaxies, the more we find these black holes, and the inventory is rising high. So any idea for the formation of a galaxy will now have to include some explanation for how you get a black hole in its center.
So how did every big galaxy in the universe end up with a giant black hole in the middle? To understand, we have to go back to the very beginning. The Big Bang.
You got the Big Bang handing you your birth ingredients, your hydrogen, your helium, your traces of some other elements. So it's kind of like this soup. You put it together and stir it.
The main stirrer for the soup is gravity, drawing together wisps of hot primordial gases. Over time, the clouds of hydrogen gas cool down and grow more and more dense, until some coalesce into the first stars. These are giants, hundreds of times bigger than our sun. They burn out quickly and dramatically in the flash of a supernova. What's left at the core is a black hole.
Perhaps the black hole becomes the seed from which the galaxy sprouts. the gravitational seed that is used as an attractive force to accumulate the rest of what we would today then call the greater galaxy.
Possibly seeded by black holes, the infant galaxies dance and orbit one another as gravity pulls them closer. So our Milky Way galaxy, as this time-lapse simulation shows, was not born in one single event. Instead, it was built over billions of years from a swarm of smaller galaxies smashing together, merging.
But if another galaxy comes too close, they will each feel each other's gravity. And in that collision, what started out as a stately ballet of stellar orbits moving around the center of their galaxy has now become this maelstrom. There's no other way to say it. Galactic cannibalism, that's what they're doing. They're dining on their neighbors, eating entire galaxies. Well, for every galaxy you eat, if that galaxy has a black hole in its center, it's going to eat the black hole. The black hole will work its way down to the center of the large galaxy, making the center of the galaxy bigger as well as the galaxy itself. It's just that simple. The big galaxies get bigger, and the little ones get eaten.
Galactic cannibalism is how galaxies grow, and with them, the black holes at their centers merge and grow bigger. But what does the presence of such a monster mean for the life of a galaxy? Brian McNamara believes he's found the answer, and it isn't pretty.
That's it right there. We got it. That's it. Okay, so you want to go...
McNamara studies the life cycles of the universe's biggest structures, galaxy clusters.
There it is. That's the galaxy. So that's what we've been looking for. This is the giant central galaxy in a galaxy cluster. And each one of these little dots here on the screen is a giant galaxy as big as our Milky Way, maybe even a little bit bigger. And they're all bound together by their own mutual gravity. So they're all buzzing around this giant galaxy like bees buzzing around a hive.
McNamara probes his galaxies with multiple tools. Optical telescopes, radio receivers, even X-rays.
Oh, there we go. Check that out.
X-ray images reveal a vast cloud of hot gas through the whole cluster, across hundreds of thousands of light years.
There's an atmosphere of gas that pervades the entire galaxy cluster, and it's an atmosphere like our atmosphere, except that it's far less dense and it's much hotter.
But when McNamara looked at X-rays of the gas around certain clusters, he saw that vast clumps of it appeared to be missing.
I was blown away. I'll never forget the moment we got the observations, and lo and behold, these two giant cavities showed up in the X-ray emission.
The size of the cavities was astounding.
That's 200,000, 600,000 light years from end to end. So between that cavity here and this cavity here, we could stuff 600 Milky Ways in there. It's just astonishing. The energy involved is huge.
Something powerful had pushed the gas away, across vast regions of the universe. McNamara traced the power source to the center of a giant galaxy, a supermassive black hole.
So we could see the beam coming out of the black hole and ending up in these big cavities.
But how can a black hole, a creature famous for devouring everything within its grasp, spew energy across the universe? The answer lies in the way matter falls toward the black hole. It turns out, nothing goes straight in.
As matter falls in, what we know now is that it spirals around in a disk, okay, very much the way when water goes down the drain. It doesn't just go straight down the drain.
Just as water spirals down a drain in a whirlpool, matter and light spiral at high speed into a black hole,
And the speeds that matter can achieve around that black hole approach the speed of light. And when matter travels at that speed, it gets a tremendous amount of energy.
Matter falling into a black hole is a lot of stuff trying to get into a very small place. And so it's like trying to fill a dog dish with a fire hose. Most isn't going to get in.
The black hole chokes on the influx. And the high-speed whirlpool of matter produces a powerful magnetic field, coiling around the black hole and shooting the energy outward. These enormous jets of energy, hundreds of millions of times the power of the sun, can blast right out of the galaxy.
There's no question that the black holes at the centers of galaxies have a profound influence on their surrounding. They send out these huge jets moving at almost the speed of light. And those jets can send shock waves into the surrounding medium and change their surroundings completely. They have a dramatic influence.
Not only can they blast away huge quantities of gas, but they may even sterilize the galaxy so new stars can't form.
The supermassive black holes at the center may be responsible for limiting the size of galaxies. In principle, galaxies can grow to very, very large sizes, and what we see in the universe is that they don't. And we think that the supermassive black holes at the center may be the culprit. They may be responsible for preventing runaway growth of galaxies.
We usually think of black holes as God's dumpster, but they really are actors on the galactic stage.
If supermassive black holes can wreak so much havoc, what's to stop our own monster of the Milky Way from wiping us all out? It all depends on the monster's diet.
Most of the time, a black hole isn't eating. It fasts more than it feasts. But when a black hole feasts, it can have a tremendous effect on the surrounding galaxy.
The more black holes chow down, the more matter and energy will blast outwards.
One of the key differences between galaxies with supermassive black holes is whether or not their black holes are lit up, because they're basically binging on a lot of material in its surroundings.
For years, our black hole seemed to be fasting, and the Milky Way was peaceful. But in 1999, the Chandra Space Telescope detected a powerful signal from the galactic center.
Station 34, Chandra OC.
An explosion near the event horizon. Is this the beginning of a black hole binge? For trackers of the galactic center, the blast is a wake-up call.
There was a hot piece of news. A remarkable fact for all of us was, for many years, how inactive the black hole was. And all of a sudden we saw, well, there's an object there which wasn't there before.
Reinhard Genzel has been watching the galactic center for nearly 2 decades. Like Andrea Ghez, he's been tracking the orbits of stars, helping to prove the existence of a black hole at the heart of the Milky Way. Now both Genzel and Ghez will shift their focus and try to measure the black hole's appetite.
One of the big mysteries about the black hole at the center of the galaxy is when we see emission matter falling onto the black hole, or rather the black hole eating up its surroundings.
Genzel and Ghez are joining a worldwide effort. Chandra in orbit will take X-ray pictures of the galactic center. At the same time, 5 major observatories on the ground will probe the black hole, all trying to count calories. Genzel heads south to Chile, while Ghez and Becklin climb a mountaintop in Hawaii. Telescope time is precious. There's no room for mistakes.
When you're there, it's an incredible rush. I mean, you're very much on for the few nights that you're there, hoping the weather cooperates, hoping that the instrument cooperates.
How's the Yak 4 look on the oscilloscope? Does the timing look okay?
Better now.
Okay, let's see if there's something there. Madeline, we're ready to go?
The teams have 5 short nights to find out how much the black hole is eating by measuring the energy that flares out.
Zoom in a little bit more. All right, so first night. Doesn't look like we've got any flares.
Chandra headquarters in Cambridge, Massachusetts. The first night turns up only noise.
4 more chances, guys.
Night 2. Chile has problems.
No, we have to redo the acquisition over.
Even if there are flares, the Chilean telescope can't see them.
The correction was
unstable.
Yeah, unstable.
A patch of humidity is confusing the computers. The crucial adaptive optics aren't working, and everything's a blur.
Extremely.
Okay, now we have a problem with the 8-meter, with the main mirror. The 8-meter mirror seems to be deformed.
In Hawaii, it's not much better for Gez and her team. The Galactic Center is playing hide-and-seek behind overcast skies.
We're fighting with clouds. It looked better just a moment ago, so it looked like we were just ready to go, but now it's looking like yuck.
The Hawaiian forecast predicts even more clouds tomorrow. The team is getting anxious. Finally, on night 3, the German team's luck changes.
They're in correction.
Look at this. Right. It's really flaring. To calibrate.
In Chile, they spot an outburst.
That's the best flare event that we saw during this run. Definitely.
A new point of light appears in the starfield, one that wasn't there before.
Very nice, very nice.
Here we can clearly see a region between those 2 sources where there is no other object. And here we have the same region, the same 2 sources, and now in between we see an additional source. So this is the flaring state of Sagittarius A star.
JPL-COM, Chandra OC.
When the Chandra team downloads their data from space, they see it too.
Oh, yeah.
The X-rays show a spike that coincides with the Germans' flash of light. Genzel checks in with the Hawaiian team, but they're in the wrong time zone.
News from our colleagues, of course, telling us that they are a few hours further west, so the sun hasn't even set yet.
The Galactic Center hasn't risen above the Hawaiian horizon, and Gez has missed the flare.
This part kills me. Waiting.
But the next night, Gez finally gets what he's looking for.
Like that image a whole lot better.
Really? Yeah. Really?
So in fact, we can see flaring activity where we think we're seeing matter fall into the black hole. And just a few minutes later, it was absolutely gone.
This now you see it, now you don't flash of light is an explosion of energy produced when matter rushes toward the black hole and some escapes.
We were taking measurements and you didn't see anything from the black hole. All you saw was a star, and then bam, it was there and bright. And 15 minutes later, it was gone. So that was our moment to make the measurement, and it was extremely exciting to know that we'd actually been able to catch it.
The teams are thrilled to capture a handful of flares at the heart of the Milky Way, but they're just snacks. Nothing compared to the giant jets seen in distant galaxies. What's more, they're looking like rare events. There's simply not enough matter near our black hole to provide a large continuing feast. It seems, at least for now, the giant's plate is empty.
Our black hole had a wild teenage life. I'm pretty sure of that. It all had jets. It threw a lot of matter out. It had a grand old time. And now it's decayed into the old folks' home.
But what would it take for the monster of the Milky Way to come out of retirement? Could explosive jets of energy blast across our galaxy in the future? Tantalizing clues are turning up in the coldest place on Earth. A Smithsonian team is tuning into high-frequency radio signals from the galactic center. The best reception is at the South Pole. Not as nice as Hawaii, but the date is worth it.
There's some of the gas falling in toward the black hole in the galactic center.
Reading the radio signal, Anthony Stark detects just small amounts of gas feeding the black hole. Nothing too serious, but farther out, about 400 light-years from the galactic center, he can see signs of something much more alarming. A vast ring of matter is gradually growing bigger.
This storage ring then builds up until it coagulates into a single gigantic cloud of about 30 million solar masses.
When the ring reaches a tipping point, it will condense into a giant cloud, triggering a dramatic starburst event, a storm of stars forming and dying quickly. What's left of the gas cloud will spiral down into the grasp of the black hole,
which then rapidly spirals in and feeds the black hole in the galactic center, making the Milky Way an active galaxy.
When the feasting starts, the fireworks will be seen across the Milky Way. But don't bother marking your calendar. Dinner time isn't scheduled for at least 10 million years. The Milky Way will survive its black hole's upcoming feast, but it isn't likely to survive the threat further down the road: galactic cannibalism.
Our galaxy, the Milky Way, is not immune from these colliding galaxy scenarios. We've got neighbors.
2 million light-years away, our closest neighbor, the Andromeda Galaxy, is charging toward us at almost 700,000 miles per hour.
We're falling towards each other, and one day we will collide.
Knowing the galaxy's dimensions and the laws of gravity,
what our simulations show is what could happen basically in quite a few billion years from now, when the two galaxies will actually approach each other and merge.
the merger will take more than 2 billion years, while the galaxies circle and entwine.
Imagine what that might look like from another galaxy. They'll see two grand, beautiful spiral galaxies moving towards each other, slowly losing their shape. They'll see new avenues where stars and gas can funnel down towards this newly formed center, feeding this reborn monster.
The collision will send a blizzard of stars and gas in all directions. Some will shoot toward the crowded core of the new galaxy, spurring massive explosions.
In the process of merging, there will be a very strong starburst event occurring at the time of the merger as all of the gas is being funneled towards the center.
Amid the turmoil, chances are our little solar system will either witness a spectacular show or be flung out of the galaxy into the voids of space. The Milky Way will be destroyed. But what about the black hole at its center? Most likely, it will merge with Andromeda's, a monster 50 times larger. Stars and galaxies may come and go, but supermassive black holes just get bigger. Once considered freaks of the cosmos, black holes are coming into their own, claiming their place center stage in a violent, changing universe.
As we forge ahead in trying to understand how we came into being and how all of the matter got put down in the universe, we can't leave black holes out of the picture because it seems they play a fundamental role on very, very large scales.
Black holes not only wreak havoc upon the landscape in which they're embedded.
Object was really an amazing achievement.